Okay, hello and welcome everyone. So in this video, I'm going to introduce the idea of value functions, in particular the indirect utility function, and I'll talk a little bit about substitution and income effects. All right, so far we have seen the consumer's utility maximization problem, where the consumer is trying to maximize utility subject to some budget constraint with the following solutions. So the optimal demand for X, this is Marshallian demands, as a function of the price of good X, price of good Y, and then the income, and the optimal demand for good Y as a function of price of good X, price of good Y, and then the income. So I say these are our familiar uncompensated, or the terminology I've used is Marshallian demands. And this is what we get as a result of the consumer's utility maximization problem. We saw this for Cobb-Douglas, for perfect substitutes, for perfect complements, and for quasi-linear. Here's an example with Cobb-Douglas. So suppose the utility function is just this simple Cobb-Douglas, where my utility is just the product of my amount of good X and my amount of good Y. The Lagrangian would be a function of X, Y, and lambda. So I'm going to try to maximize this objective function, my utility function, subject to this constraint. So if I take the partial with respect to good X, this is going to be Y minus lambda px is equal to 0 is the first order condition. Partial with respect to Y, X minus lambda py is equal to 0. And then my partial with respect to lambda, penalty for violating the constraint, is just the budget constraint. And then solving really quickly, we recognize on the left-hand side, well, this is the MRS, y over x. And then the price ratio, px over py, so that's going to do something like this. Now, look what I've done. I've solved first for lambda, then I've substituted. This is the marginal utility of x divided by the price of good x, marginal utility of y divided by the price of good y. Remember, marginal utility is just the partial with respect to that good. So this is literally our bang for your buck condition. Marginal utility of x divided by the price of good x, marginal utility of y divided by price of good y, where this is equal, we have our tangency. And this is telling us that we've optimized. Anyway, or when this is true, then the consumer will have optimized. Anyway, so then what I've done is I have cross-multiplied to get literally the marginal rate of substitution equal to the price ratio, or you could have just skipped ahead. You could have said, oh, it's going to be, draw a line here. This is going to be MRS is y over x. Price ratio is px over py. Good. Either way, we're going to have something to substitute into the budget constraint. Most efficient way to substitute is for the entire expenditure for one good. So you don't need to solve this just for X or for Y. That's going to invite a lot of algebra. You could just substitute for the expenditure on Y, that's this, or the expenditure on X. Here I'm going to substitute for one or the other. You can kind of visualize this. If I substitute for the expenditure on Y, I'm going to have PXX plus PXX, or 2PXX, and then dividing through my demand for good X is going to be income divided by twice the price. And then my demand for good Y, income divided by twice the price. Remember, our generic Cobb-Douglas demands are going to be for alpha, or for X, it's going to be alpha over alpha plus beta times M over PX. Well, here, alpha and beta are both 1, so it's going to be 1/2 income divided by the price. Okay, so that's consistent with this. Now, here's my note. If we substitute the demand functions back into the original utility function, we get the indirect utility function. In general, for our constrained optimization problem, once you get these optimal solutions, if you plug them back into the objective, you'll get the value function. In this case, the objective function was the utility function. That's our objective. We're trying to maximize utility subject to this constraint. We've got our solutions. Let's plug them back into the objective. That'll give us our indirect utility function. So here were our solutions, and I'm going to evaluate my utility function at the optimals. So here I've done that. So my value function is going to be m squared 4px/py. This is our indirect utility function. It's a utility function. However, it's given us the maximum utility attainable for a given set of prices and income. It does not take the actual amounts of X or Y as bundles, or the bundles as its arguments. So this is why it's the indirect utility function. You can think for implied work, maybe you see the prices, maybe you see income, and then you can back out indirect utility or whatever. So the value function is where you take the objective and you evaluate it at the solution. So here the value function is the indirect utility function. I've just taken my X star, my Y star, plugged this in here, and then cleaned up, and I've got my indirect utility function. All right, well, the consumer actually faces a dual problem. We can think of optimization relative to minimization. Suppose the consumer is trying to minimize its expenditure. So here would be the consumer's expenditure minimization problem. The consumer is choosing X or Y. These are the amounts of good X or good Y to consume. in order to minimize its expenditure. Here's the expenditure on X, here's the expenditure on Y. This is its total expenditure, subject to, well, the constraint now is, given my preferences, how do I hit this level of utility? Right? So this is choosing to minimize expenditure subject to the goal of hitting some utility level. So here would be the example with our Cobb-Douglas preferences. So the Lagrangian would look similar, only kind of reverse some things. My goal is to minimize, right? Minimize my expenditure subject to the constraint. Now the constraint is my utility function minus this fixed level of utility. Everything else is going to look really similar. The derivative is going to turn out the same, but in different order. So it's going to be the px minus lambda p or lambda y is equal to x, or is equal to 0. And my partial with respect to y is going to be py minus lambda x is equal to 0. Here's price ratio, px over py. Here's MRS, right? And then if I solve for lambda and then substitute, or however, you're going to end up with the same tangency condition, right? The minimization and the maximization problem are going to give us the same result with the same utility function for a fixed level of utility. And so here, my tangency is still where my expenditure on X equals my expenditure on good Y, given this utility function. And now I'm going to go substitute. However, remember, for optimization, we are always substituting into the constraint. So the place where people might mix this up is for the minimization problem, you might try to plug into this part, because we always plug into something that looks like this. No, we always plug into the constraint, right? So I'm going to take my tangency condition and I'm going to evaluate my constraint at that relationship. So I'm going to plug this into the constraint, which is xy minus or is equal to fixed level of utility. So here I've substituted for x, this stuff. I've just got y's, I'm going to solve for y, and this is going to give me, this is a demand, this is going to give me my optimal level of y. I can do a similar substitution into the constraint to solve for x. This gives me my demand for x. These are still demands, though the outcome of the consumer's expenditure minimization problem is our Hicksian demands, our compensated or Hicksian demands. These give me my optimal amounts as a function of prices and this utility level. We can replace these optimals into the objective function. Now the objective function is this part. My objective was to minimize my expenditure, so I'm going to plug these Hicksian demands in for this x and then for this y. This is going to be x star and y star, and that is going to give me my consumer's expenditure function. Right, so my expenditure function is going to be px and then substituting for x star, py, substituting for y star. And if you clean this up, the algebra is a little bit annoying, but if you clean this up, you get something that looks like this. This is the value function for the consumer's expenditure minimization problem, analogous to the indirect utility function that came from the consumer's utility maximization problem. Now let's see a numeric example. So So what the consumer is trying to do is maximize the utility. It's the most utility possible given this utility function, given these prices. Let's take the same Cobb-Douglas preferences. Suppose the price of good 1 is 1, price of good 2 is 1, and we have 8 for income. So I'm gonna still leave these preferences. My alpha and beta are still gonna be 1. This is gonna give us enough moving parts, but not too many to be able to see what's going on. So here would be my Lagrangian. Here is gonna be my first order conditions. And then since P1 and P2 are both 1, this is the same condition from above, right? Where we are getting, this is our minimization problem. We are getting at our tangency, the expenditure on y is equal to the expenditure on x, but P1 or Px and Py are both, said that backwards, but the prices are both 1. All right, so that's what's happening down here. Sorry for scrolling, I just made myself dizzy. So I wanted to be a pilot, but then I realized I get airsick. So though I want to be able to fly to campus because that'd cut down my commute, can't do it. So, all right, here is our tendency. I'm going to evaluate the budget constraint and then solving my Marshallian demands. This is going to be x1 plus x1, or 2x1 is equal to 8, or x1 is equal to 4. x2 is going to be equal to x1, so x2 is also 4. So my Marshallian demands for good 1 and for good 2 are both 4. Let's evaluate my objective at the optimals. It'll be 4 squared, so that is 16. Is my indirect utility function evaluated at the optimal, gives me my indirect utility. All right, now let's do the dual. So here's the cheapest way to hit a utility level of 16 given those prices. So I'm going to minimize my expenditure such that given my preferences, my utility is 16. So here's this differentiation. Here's my first order condition. Again, I get the same tangency condition. I'm going to evaluate this by plugging into my constraint. My constraint is now the utility portion, of course. It's always what's multiplied by lambda in my Lagrangian. And I come up with x1 squared is equal to 16, or my Hicksian demand for good x, good 1 is 4. Demand for good 2 is also 4. In my expenditure, let's evaluate my objective function at the optimal. That'll be 4 plus 4 is 8. That is telling me the minimum expenditure to hit 8 or 16 units of level of utility is 8. It's my expenditure function. Well, of course, it has to be, right? Because here's what had happened. I had 8, my income was 8. These were the prices, this is my preferences, and the utility level that I got, indirect utility, was 16. And now the cheapest way to hit 16, if I was optimizing, has to be with those prices and with these preferences, has to be the $8 I had available. Right? So the problem is the same for a fixed level of utility and for a fixed income. Here's a little bit more about those compensated demands. Generally, utility decreases when prices rises. Suppose when the price changes, the consumer's income was hypothetically adjusted to keep them on the same indifference curve. This lets us separate out the substitution and the income effect. So this would be, here's one picture. Here is where the price changes. So here is our original budget constraint. The price of good 1 doubles, so I can buy half as much. Or let's just say it rises. Maybe I don't need to say it doubles. So either way, my budget constraint becomes steeper. I can consume less of good 1 or good x. I'm on a lower indifference curve. The price changes causes a change in utility, namely a decrease in utility. Well, suppose we compensated that price change. Suppose when the price of good X rose to here, suppose we gave the consumer enough income to be back at their old utility level. To get back to the original indifference curve, the tangency is going to be way up here. We're just like hypothetically spotting them enough income to get back to the same indifference curve, albeit where the tangency is going to be equal to a steeper price ratio, right? So that's the compensated price change. In a later lecture, I'll talk a little bit more about compensated price change and kind of why we care about it. Ultimately, what this does is this helps us illustrate the income and substitution effects. The substitution effect, that's the effect on the consumer's choice of changing the price ratio, leaving the utility unchanged, right? Relative prices change, so I buy whatever is the relatively cheaper good. That's purely the substitution effect. The income effect is the effect on consumer choice of changing the feasible set, changing the budget set, leaving the price ratio unchanged. So this would be spotting me enough income to be able to, so then this is capturing the effect of the change in consumer choice because I'm now relatively richer or poorer when I try to buy that good because the price has changed. All right, here's an example to isolate those things. Suppose I have perfect complements preferences. My utility over good 1 and good 2 is going to be the smaller of good 1 and 3 times good 2, my amounts of good 2. Find the demands when the price of good 1 is 3, price of good 2 is 1, and my income available is 40. Find the demands when price of good 1 and 2 is both 1, and my income available is 40. Now find the income that is now required by the consumer in order to consume the original bundle, consume what I consumed at part A at the prices of part B. That's what part C is asking us to do. Call this income M hat. Now find the optimal bundle at the new prices. When the consumer has the income that we found here, what would they buy at the new prices? Using the values you just found, calculate the numerical values for the substitution and income effects. Substitution effect, again, is the change in consumption due to the price changes when purchasing power is held constant. The income effect is the change in consumption due to purchasing power changes when the price is held constant. What do you observe? I'm going to put this back up here. You can take a look at it. I mean for this actually to be a teaching example, so I'm going to go through it right away. Okay, so, and this is the last exercise on the IMX, I think it's like IMX exercises. It's on a different playlist for IMX 1. All right, so when my price of good 1 is 3, price of good 2 is 1, my income is 40. Here's my budget constraint. Remember how we do these perfect complements. We replace the comma with an equal sign and then solve for x2 gives me the line x2 is equal to 1/3 x1. And I'm going to evaluate my budget constraint at that point or substitute for solving for x1 and then is going to be 3x2. I guess that'd be the easier way to do it because that's what I did. So we'll have 9x2 plus x2 is 40 or 10x2s. So x2 is 4. If x2 is 4, to exhaust my budget, I'd have to get 12 units of good 1. Now at the new prices, where the price of good 1 is 1, price of good 2 is 1, and income available is 40, my budget constraint would be, let's see, x1 plus x2 is equal to 40. And my price ratio again was, or not price ratio, it's going to be x1 is equal to 3x2. If you substitute in, let's see, I will have 3x2 plus x2 or 4x2 is equal to 40, so x2 is equal to 10, so x1 has to be equal to 30. So this is the bundle that I will get at the new prices. Now, in order to obtain the original bundle, where I had 12 good 1 and 4 good 2, at these new prices, I only need $16, or 16 units of income. 1 times 12 is 12, 1 times 4 is 4, so that's 16. So that was part C. Now substitute my relationship into my new budget constraint. Let's build a new budget constraint. Let's take the income that I would need hypothetically to afford the old bundle at the new prices. Let's actually take that income and let's take the new prices. Let's build my new budget constraint. X1 plus X2 is equal to 16. Now let's substitute in this relationship. So I'll have 3x2 plus x2 is 4x2 is equal to 16, or x2 is 4. If x2 is 4, then x1 is 12, because 4 times 3 is 12. And so what would happen if the prices was 1 and 1, and if my income available is 16, I would buy 4 units of good 2, 12 units of good 1. So now what I've done is I've done original prices, bundle at the original prices, that's this. Then I did the bundle at the new prices. Then I said, hypothetically, suppose I only had enough money to buy the original bundle at the new prices, that'd be 16. Now let's build a budget constraint where I have the new prices and the old, in the hypothetical income. Let's see what I actually buy. So now we can compare these. So for part E is saying, using the values you just found, calculate the numeric value for the substitution and income effect. All right, so what we want to do from part A, that was my original prices, original bundle. Part C and D gave us the new income, new prices. The substitution effect is just how much the consumer changes consumption of good 1 in response to the change in price while holding purchasing power constant. Holding purchasing power constant means I'm going to compare where I had the original income at the original prices, and then I'm going to compare the analogous sized income at the new prices. I'm going to compare my bundle where I at the old prices, where I had price of good 1 was 3, price of good 2 was 1, and my income available was 40. I'm going to compare that to the analogous situation where I have the same purchasing power, where the prices of good 1 is 1, price of good 2 is 1, and I have 16 units available. So that's this right here. And if you look, I bought the same amount of good 1 in both cases, right? Even though the price of the good changed, the substitution effect was 0. And that's got to happen because we have perfect complements preferences. The substitution effect is just how much the consumer changes consumption of good 1 in response to the change in price, holding purchasing power constant, which is what we do in the comparison between part A and part D. So since I buy 12 units in both cases, we know the substitution effect is 0. The price of good 1 changed, but I still bought the same amount of good 1. I have to, because these are perfect complements preferences. Now let's find the income effect. Here we're interested in the change in purchasing power given the change in income from 40 to 16, holding the prices constant at the new price at 1 and 1. The change in consumption is then given by the change in good 1. So this is going to be 30 and 12. Why? Because when I had 40 units of income available at the old prices, I bought 12 units of good 1. At the new prices, let's see, what are we comparing? New prices. Sorry, I lost myself. Change of good 1. So we want to compare. Find the income effects, change of good 1. We have the new prices, the original bundle, original income, minus the new bundle and the change in prices. So that was where we had the 30 and the 12. So here's our 12, and here was our 30. So we're comparing B to D, right? So here we have our new prices, old income, and now we are comparing this to the new prices with the same purchasing power, and so we have 12 and 30, and so the entire change is, it's 30 minus 12, so that's our 18. So the entire consumption response is coming through the income effect. Of course, because there's no substitution effect because our preferences here are perfect complements. So I've got a follow-up video, and I go through this again in the intermediate micro exercises 1 at the end of the IMX1 exercises. There's another walkthrough of this. But anyway, I hope you enjoyed the video, and I'll see you next time.